Hello, I'm David. It's semester 1 2018. This is Multivariable Calculus Revision Seminar, and that'll do. Well, welcome. I'm sure I did multivariable calculus when I was a student, but most of the stuff I remember about it has happened through helping people in the Maths Learning Centre, which is my usual way of remembering everything. That's why I'm so good at Maths 1B. Do it 3 times a year. Right. I've been asked by a couple of different people to talk about various integrals. How does everyone else feel about that? Okay, good. Okay. I assume nodding means that you actually would like me to do that as opposed to you just understand what I'm saying. So, okay. And I had a couple that are past exam questions, which people sent me and will come up shortly, that might help me to guide what I have to say. So I'm going to just look them up and hopefully we can sort them out. All right, well, integrals. Okay. So I'm just going to talk a bit generally while my thoughts are sorting themselves, and hopefully we'll get something good out of it. In multivariable calculus, you can only integrate a number. That's the first and most important thing to know about the way integrals work. So the concept in my head of the way integrals work in multivariable calculus is that you add up a number across some sort of path or surface or region in space. And the important thing is that it has to be a number. And so some of the integrals have vectors in them, but if you look very closely, you create a number out of those vectors. You can only integrate a number, which means that the thing that is next to the integral sign has to produce a number in order to be able to do the integral. So you will have some number of integral signs. Number. That's, you know, how the whole thing works. And this number includes the d, like the ds or the dv or the d whatever. Okay, that's my first thing. And when we say add up, we're sort of taking into account that if the number is more often a certain value, then it counts more. And so if it's mostly close to 3 across a large region, then you'll get a lot more 3s in your answer than then your answer would be closer to 3 than it would be if it was less than that. So cool. Right. Which means that if you want to think units, the integral of number is always one dimension higher than the number of integrals you're doing. So if you do the integral of something, then the triple integral of a number, then what you have is technically a 4-dimensional thing. Okay. Right. That's good to know. Whoa. Okay. So that's what we're doing. And it's important to realize that what we're not calculating is areas, lengths, or volumes. They are extremely special cases of the thing we're calculating, but we're not calculating areas when we do a double integral most of the time. Okay? Most of the time when you do a double integral, you're calculating a volume, not an area. So here's the idea. Here's a path, and at every value, at every point on that path, there might be a number attached that you can, based on what point the path is at, some sort of formula usually that tells you what number it is. Maybe it's a scalar field. And what you're going to do is you're going to take all those numbers and you're going to add them up. So maybe at this point the number is 1, and at this point the number is 2, and at this point the number is 1 again, and at this point the number is 3, and all of those values will have a number of their own. Maybe it's 4 here. I really shouldn't have put a loop in it if I was going to do this. All right, every point has a number of its own, and you interpret them as heights, and then you add them all up. And so I'll take all of these numbers, and I will interpret it as a graph, and I'll add up all those areas, and it will produce an area. That's the idea behind it. Okay? Cool. So now I can't draw Cuisenaire rods on the finished version of this, so I'm just going to do it like this. So at every point maybe there's a number. Maybe the number is 1 here, 2 here, 3, 1, 2, 3, 1, 5, 2, 7. And then what you can do is you can add them up. So 1, 2, 3, 1, 2, 1, 3, 5, 2, 7, 2. Right, something like that, and you add up the areas, and that's what you get. Now what I'm using here, which I didn't talk about, is a model of function where you're used to seeing functions as graphs, which is only one of the 3 ways to think about functions. And one of the most useful ways of thinking about function in multivariable calculus is that every point has a number attached to it. Okay, I think of it like a chocolate advent calendar. There is a window at every point, and you open it and it reveals what is behind it, which in an advent calendar is chocolate, but in this is a number. Okay, and it's there whether you calculate it or not. And what you're going to do is, as you track across that number, you're going to add up all that chocolate, and it will give you an area, or a volume, or whatever it is. Okay, so it may be that instead of this, you have some sort of region, and every point on the region has a number attached to it as well. In which case what you're adding up is not a line of these heights, but a region with heights above it. Okay, so every one of these, maybe this one's 1 and this one's 2. Like that, and everything there is there, and what you can do is you can make a grid. So this is imagining a surface in 3D, and every point on it has a number, and you can make a grid and go 1, 2, 2. I just felt like playing with Cuisenaire rods today, so 4, 5, 5, 2, 1, 0. What colour is 6? Right. I missed one. No, I didn't. And I have this thing. Whoa. There we go. Something like that from this angle. Oh wow, this is really confusing. All right, that'll do. And what you're doing when you do the integral of all these numbers is you're getting a volume. Okay? Now in 4 dimensions, in 3D, when you're adding up numbers across a 3D thing, technically it's a 4-dimensional volume, hypervolume. But we're not going to go there. And so I can imagine this more like this. This is not that graph. cut and paste a screenshot in this spot, really. That would be useful. And so on. I'm not going to draw any more of it. Okay, it's a volume. Okay, that's the idea. Cool. So, anytime you integrate anything, that's what you're doing. If you want to find out what the area of a surface is, you just need to make all of the heights 1, in which case the volume will be area times 1, which is the same number as the area. And even though it's technically a volume, it's the same number as the area, and so it calculates the area. So that's the basic idea. But in multivariable calculus, you don't always just have numbers at every point. It may be that at every point in space, what you calculate is, what you find is a vector. Behind your advent calendar window, there's not a number, but an arrow. Now, that arrow doesn't live in the same land that the other thing lives. It's fixed at that point and points in a certain direction and has a certain length. But we normally think about it as a set of coordinates. And when you are doing integrals, you're usually figuring out you're not adding up the arrow itself, you're adding up how much the arrow points in a certain direction. You're figuring out the length of the component of that arrow that's in a certain direction. So when you do this thing, and maybe at every point behind the advent calendar window there is an arrow, like that. You're not, when you do the integral of that arrow across this line, you are not integrating the arrows themselves. You are just figuring out how much of the arrow is pointing in the same direction that the line is currently going. So as I track this line forward, the line's going that way, so I figure out how much of the arrow is in that direction. This one's going backwards relative to the arrow. I might do that in a different colour. Come down here, that's forwards. That's hardly any. This one's 0. So at any given moment, I can figure out the arrow, and I can figure out how much of the arrow is in that direction, and that is the number that I integrate instead. So if I wanted to do this, the integral of my function across my curve, is it ds? Yeah. There's a dot here. Okay, this is a vector field. I shall call it. What does your lecturer normally use for this symbol? Sorry? Yeah. And it's a vector as well, right? Okay, so you have to put a dot here because the dot product tells you how much of something is in the same direction as another thing. And that thing here is a number. And what that's doing is that the function value, which is a vector, it's figuring out how much of it is currently pointing in the same direction as the curve. Right. That's just some general thoughts, and what we'll do is we'll actually calculate some of them, and it'll all make a lot more sense, hopefully to me at least, when we do that. Cool. All right. One more thing. Something that happened here that you may not have noticed is that in order to do this integral, I had to unravel this line. And in order to do this integral across this surface, I had to flatten my surface out. And what that means is, in order to draw this grid, I had to have a grid which was sort of curved, but I had to draw a grid on my surface and have coordinates that tell me which point in my surface I am up to based on 2 coordinates. And in this one, I had to have a number that told me which point on the curve I was up to. So you need to have a parameterization, usually, of a surface or a line or a volume in order to do this. because you have to be able to know when you're adding up across a line which point on the line you're up to at the moment. So this here might be a parameter t, which tells you where I'm up to on this line. And an important thing to realize is that mine, while it may look here that it's drawn evenly spaced along this line, evenly spaced along here may not correspond to evenly spaced along here. It may be that this is moving twice as fast as this is. It may be that here, that when I'm here, this is moving really slow, but when I'm here, it's moving really fast. So because the point on the curve is moving at a different speed to this, I need to take that into account when I figure out the area. And what that is this ds, therefore has inside it an idea of how fast the curve is moving at the moment. And so when I do this, it becomes like that, where gamma is the function which describes where I'm up to on the curve. Did they use gamma in your course? Good. Gamma is good because it's the third letter of the Greek alphabet, which goes with the third letter of the English alphabet, C for curve. So gamma for curve. That's why they use gamma. Because gamma in Greek can either make a g or a k sound depending on where it is. So, okay. So this thing here, I think about this, that ds and you did that when you did derivatives, actually. So this ds is a change in the position on the curve, right? So when the t moves by a little bit, the position on the curve will move by the tangent vector like that. So I'm just going to talk about this for a bit. I didn't have a particular plan to start with. I wish I had, but I didn't. So I'm sort of making this up as I go along. The idea is that here is the possible values of t, here is my curve. And so every value of t produces a matching value of position on the curve. And so when the t moves by a little bit, that's the dt. The s will move by a little bit, that's the ds. But this dt is a number, and this ds is a vector in space. And that ds is a multiple, well, it's pointing in the current direction of the curve, so it must be a multiple of the vector, tangent vector, which is what this is. And that's why it is the way it is. So all derivatives are like that. D of the thing in the target space is something times D of the thing in the beginning space, and it needs to be the right kind of thing to produce the correct object. This is a vector and this is a number. The only way to multiply a number by something and produce a vector is to multiply it by a vector. That's why when you do a derivative of, if you go from R2 to R3 and you do a derivative, you'll get a matrix, because you have vector in R3 equals some multiple of vector in R2, which means the only way to do that is to put a matrix in that spot. All right, cool. And all of it works on this, and everything hinges upon being able to produce parameterizations for things. Okay, good. Now that my computer is working, I might be able to actually get up the thing I need. Okay, which question was it? In 2016? Or were you doing, did you ask about 2016? Okay, you asked 2013. Okay. Everybody who has asked me questions for the last 2 weeks has had a name starting with J. It's made it quite difficult. Which question was it? Yeah, that one. Okay. Mum? The lecturer in 2016 was extremely helpful in the way they labelled their exam. I actually told you at the beginning what it was about. That's like so friendly. Oh, so, okay, good. Which means next year will probably be a different lecturer. They normally have the lecturer for 3 years in a row and then you switch over to someone new. But that won't matter to any of you. It will matter to people who are listening online next year. Okay. Volume of W, flux integral. Wow, all sorts of fun stuff going on there. Okay, so the key to understanding a lot of this is attempting to figure out what the surface/volume actually is. And having some good imagination helps, and a good support for your imagination in multivariable calculus is to see actual physical things so that later when you're in the exam and you don't have the physical things, it's easier to imagine them. Okay, so I'm just going to do this and talk about what happens as I go. And hopefully I'll be able to talk about some of the details about how those theorems behave as I do it. If you have any questions, please ask. This is your revision seminar. It's for you. If there's something that doesn't end up coming up in this and you still want to talk about it, ask, please. Okay, so I'm just going to copy this down. So we have a region in R3. It's called W, and it's the points x, y, z in R3 such that x squared plus y squared is less than or equal to z squared, and 1 is less than or equal to z, which is less than or equal to 2. Okay. Okay. Right, before I do anything else, I want to think about what this is. Okay, so one of the best ways of dealing with inequalities is to think of what would happen if they were equalities. So x squared plus y squared equals z squared. Because I've just been doing Maths 1B, I know that's a cone. But if you didn't know it was a cone, you would say one of the best ways is to pick various values of z, which is the height, and figure out what shape that is. So for various values of z, I'm just going to think about. So for various values of z, fix z x squared plus y squared is equal to z squared. Is a circle radius z, well technically radius the absolute value of z, because if z was negative it couldn't have negative radius. It's using complex numbers and then circles are way cool. Okay, and so as z gets higher the radius gets bigger. All right. Cool. Okay, so that's what it is. So I'm thinking it sort of goes like this. So this is supposed to be looking like it's flat and then the z goes up from there. And when z is 0, I get a circle of radius 0, which is just the origin. And when z is 1, I get a circle of radius 1, and then it seems to look like that. I'm pretty sure it's straight, as opposed to curving inwards at the bottom. And the reason I think that is the radius is equal to the current height, which means that if I go out in the y direction, that distance out in the y is the same as the distance up. And so that's a straight line. Okay, but I only want the bit between z equals 1 and z equals 2, so that's like this bit here. Good, good, good. And let's just check this. So that's the surface itself when it's equal to z. That's the edge. The less than or equal to z means that the radius that I'm using all x's and y's that have a radius less than that, and so it's the entire inside of this. Okay. X squared plus y squared is less than or equal to z squared is the inside. Okay. So one of the ways to imagine a surface is to imagine how it looks when you cut it at various heights and pick values for z. And I saw all these circles. You could try and imagine what it looks like if you cut it at various values of x. That is sometimes helpful, not helpful today. If I pick a value for x, then I get x squared plus y squared. I need to move the x over, and I'd sort of have x squared is less than or equal to z squared minus y squared. Z squared minus y squared would be a hyperbola, and that's not at all helpful. It is, but not helpful for what I'm trying to achieve today. Okay, circles are nice. I can deal with circles. In fact, that's a good piece of advice. Attempt to rewrite it so that you can use circles. Okay, so that's the region itself. It's the inside of this piece of this frustrated cone here. And right. So we have a transformation. Phi sends r, which is 0 to 1 cross 0 to 2 pi cross 1 to 2, into w, which is in R3, by r theta v, or is that a nu? I'll call it a v. R theta v is RV cos theta, RV sine theta, V. Okay. I reckon I could have come up with that myself. Let's just have a look at this. So, if I want to do an integral across here, I need to figure out a way of telling myself exactly which point I have within that zone. And I need to do it in such a way that's going to make my integrals easiest to do, and so that it's easiest to describe exactly which points I have. So at the moment, I've got it in terms of x and y and z. So I have the coordinates x, y, z such that x squared plus y squared is less than or equal to z squared, and z is between 1 and 2. So this gives me a nice, decent region for what z is. But given what x and y are, I have to say that the x and y have to be between like root something and root something else, and that's a bit difficult to describe. I can do it if I want. It should technically be possible to do everything I want to do and consider this as picking a z and being between like y equals root z squared minus x squared and y is minus root z squared minus x squared, and I could do all my integrals that way. But it would be much easier if I just had a zone of numbers that didn't require the other numbers to figure out what the zone is. So in this one, given a specific z, it tells me that I have to use the z to figure out what the x and the y are. But what I want to do is I want numbers that don't require me to know what the other numbers are to figure out what zone they're in. So a really useful way of doing this, the z's good, is to go just a second inside a particular circle. I can go from somewhere around the circle and I can figure out where I am on the circle. So I can go, maybe I'm at 20 degrees or 120 degrees or whatever, and figure out where I am on the circle. And that's a single number to tell me where I am on a circle. And then there's a single number to tell me which circle it is, which is what the radius is at the moment. And then there's a single number to tell me how high the circle is. And that's three separate numbers that are more or less independent of each other. And so that's what I can do. I can say that I can pick a circle at a particular height and a particular radius, and I can figure out where I am. Yes, that's what I'm doing. Okay, so let's just see. So I'm going to have height. I would normally call it h. Okay, so I would normally pick a height, and that would tell me and I'd pick a radius, and then I'd pick a position around the edge of the circle. But the problem is, there's still an issue with that. If I pick a height, and if I pick a radius, now if I pick a height of h, then z, then the radius is also z for the outside circle. But if I want to do the inside of this, I'm going to have to get the middle of that. And that means that my radii at each height are based on which z I choose. So I could choose z equals 1, and then my radius can go from 0 to 1 for the inside of that flat bit there. But if I choose z as 1.5, then the radius goes from 0 to 1.5. And that means the radius I pick depends on the height I pick, and I didn't want that to happen. I wanted them to be independent. So here's the really clever trick. Well, I just need to know what percentage of the distance from the centre to the edge I've gone. And then the percentages are always from 0 to 100%. And that's what your lecturer has done. So they've picked a height, well, a radius anyway. What's r between? 0, yep. They've picked a height, which is their v. They've picked a percentage of radius, which is their r, but as a decimal. And they've picked an angle, like a position around the circle. That's what they've picked, in the order r theta v, but I've done them in the opposite order. That's what they've done. And what that has allowed us to do is it's allowed us to say I pick a height, I pick a percentage of the radius, and then I pick a circle with the correct radius. So I know the big radius at this height is v, and then I have a small radius within that, and then a position around the circle in there. That's what I've done. So I've got the height is v, a circle would be radius sine theta and radius cos theta, and it was, the big one is radius v, but I've only got r% of that radius. And that's how he's described that parameterization. Now that we've seen it, we can use the same thing ourselves to describe things that are circles at different heights for our own purposes. Okay, sweet. Of course, all of this would have happened way quicker in the exam. It's harder when you're describing what your thought process is to someone else out loud. Okay, cool. All right, what did they call this? They called this phi. Okay, and that produces every point inside and on the edge of that, that volume. Okay, cool. Sweet. I might actually do the questions now that I understand what is going on here. Prove that the Jacobian determinant of phi at that is equal to v squared r. Okay. Do you just call it like that? No? Does your lecturer have a notation for this, or do they just... Sorry? Ah. Right, just the derivative. Okay, cool. So we want to know, when we change r theta and v a little bit, how does that change the x, y, and z coordinates? Or actually the other way around, I think. No, that's right. Okay, cool. So, just being sure that I know how this goes, we've got, no, the Jacobian's the determinant of that. Because the d is normally just the derivative. Okay, whatever. So I'm thinking that I have r, theta, and v, and it produces an x-coordinate, a y-coordinate, and a z-coordinate. Okay, so the change in the r, theta, v will be some matrix times the change in the x, y, z. This is how I think about it. I don't know if it's how they want you to write it, but that's what I'm thinking. And when you change x, y, z, it's still going to be a vector. It's a little move in 3D. And when you change r, theta, that's a vector as well. So this has to be a 3 by 3 matrix. This is a length 3 coordinate vector. This is a 3 coordinate vector. So this has to be a 3 by 3 matrix. And it's made up by how much everything causes everything else to change. So this position here should be d phi on dx. And this should be d phi on dy. Sorry, dr, damn that. Oh, for the sake of Frel, David. Other way round. Upside down, upside down. Which David will get at the back, but none of you will, because you've never seen Mr. Squiggle. Right, sorry about that. I needed to do it in the right order. This xyz is the result of the phi, and so it's the thing that that this thing causes that to change. This thing changing causes that thing to change, because that's the direction that my thing is going. In fact, I need to draw this in my head just for myself. R theta v, and phi gets here to x, y, z. So changes in this cause that to change. So I change this, I need to figure out how much that changes. All right. So this would be dx on dr, dx on d theta, dx on dv, and so on. Okay? The reason I know this is dx on dr and all of those things is that when I do this by this, it should produce a dx. So my first coordinate, dx, should be the first row times this. And so I get dx on dr times dr, dx on d theta times d theta, and dx on dv times dv, which should give you overall a dx, because it's all in terms of dx. Right. So if I really want to do it properly, I would put them all in, right? Okay. So I need to figure out what all those things are if I'm going to do this, sadly. All right. Okay, so the x coordinate is rv cos theta. So dx on dr. Okay, so everything other than r counts as a constant. We have, so the constant will still be there. Because it's multiplied on, the derivative of r is 1. And dx on d theta, the r and the v are constants, so they'll still be there. The derivative of cos is sine, only with a minus. And dx on dv, well, that'll be r cos theta. Okay, the y coordinate is rv sine theta, so dy on dr will be v sine theta, dy on d theta will be rv cos theta, and dy on dv will be r sine theta. And the z coordinate is just v, so dz on dr is 0 because there's no r's. dz on d theta is 0 because there's no thetas, and dz on dv is 1. Okay, and so I need to do this determinant, and I have helpfully for myself written the determinant in the correct order. for the matrix that it started with. Rather than drawing them downwards, I did them across deliberately so that I could get my matrix in the correct order. So the determinant of d theta d phi is the determinant of this matrix. Do I write it out? If I was in an exam, I would not write it out again. In fact, if I was in an exam, I wouldn't write this either. I would just do d phi. I might do the first one just to remind me what order everything goes in. So let's see. But I will for myself and for future readers do that. So if I'm going to do this determinant, I reckon I should expand out along the bottom row because it's got lots of zeros in it. So let's see, plus, minus, plus. So plus 0 times a times this bit, minus 0 times this bit, plus 1 times this bit. Okay. I've got that right. Plus, minus, plus. Okay, good. So that times that would be v squared cos theta squared. Note there's an r in there as well. Yep. And minus that times that, which would be minus rv squared sine theta squared. So I've got rv squared cos theta squared plus rv squared. Beautiful. So I've got rv squared cos squared plus sine squared, which is 1, which is the answer I was supposed to get. Nice of the lecturer to give me the final answer so I knew what I was aiming for. Okay, cool. If I'd been very clever, I probably could have done, row operation stuff and pulled things out, but it comes out the same. Okay. Part A, done. Beautiful. Now, I'm imagining the only reason I would want to know that would be because I want to integrate something. So my understanding of how this works is that I had d x, y, z being d phi times d r theta v. And then when I do determinants, I calculate volumes. And so a volume would be the change in x times the change in y times the change in z. That's the volume of this change, like as a parallelepiped, or however you pronounce that word. And this will be the determinant times dr d theta dv. That's what we're going to have there. So I don't know if I need, the only reason I would know I would calculate a determinant is because I wanted to do that. And so if I'm going to integrate something across all the possible values of x, y, and z within that zone, that's the same as integrating something else across all the values of r, theta, and v in that zone, but I have to multiply by this to get the correct answer, because my areas have been squished and changed. And so I need to take into account how much the area changed, because the volume that's above that area will change because of that. Okay. So in our case, it's a volume changing, and this like hypervolume that's above that volume. Yeah, whatever. Too much stuff going on. In essence, it's the same idea as moving the line faster. As I change the r, theta, and v, it moves the point across the volume faster than if I just change the x, y, and z. And so I need to take that into account. Or possibly slower. I can't remember which way around it is. Okay. Compute the volume of W. Okay. Okay, so I know that if I integrate a function across W. W is already a volume, and if I integrate numbers across a volume, I get the next dimension up, and that would be a 4-dimensional thing. But I want a 3-dimensional thing, but that's okay. If I just use the same number for everything, the number 1, it'll be the same, the answer will be the same number as the volume anyway. Same as if I want to figure out an area. If I do the height of 1, then the area and number is the same as the volume number, and so it works out anyway. Okay, so the volume of W will be the integral across W of 1 dx dy dz. So I really am calculating a volume here. Technically what I'm calculating is a 4-dimensional hypervolume, but it just has the same answer as a volume. Right. Okay, so what I'm going to do is I'm going to say that I can now say that this is the same as integrating across not W but R. Was it called R? Yes. Times that Jacobian, right? Which is on the screen. What was this? V squared R? Yep. Okay. All right, so I've flattened I've boxed out rather than flattened my 3D curvy volume into something that's a bit squarer, and I can now say that, let's see, the outermost one is V, and that one goes from 1 to 2. And the nextmost one is theta, which goes from 0 to 2 pi. And the nextmost one is R, which goes from 0 to 1. Okay, I've been careful to say which variable is which over here so that I don't get it wrong. So one step at a time. So let's see, the V squared is a constant multiplied on, so it'll still be there. And we're integrating the R, so that'll go up to half R squared. And this will go from R equals 0 up to R equals 1. And when I sub in them both, I get half of 1 squared times V squared minus a half of 0 squared times V squared. So I could probably skip that working and go straight to the answer if I was feeling comfortable. Okay. So my next one is going to be an integral with respect to theta. And I don't have any thetas, that's just a constant. So when you integrate a constant, you end up with constant times the variable. If I integrated 5 with ordinary integration with x's, I would get 5x. So I'm going to get a half of v squared times theta. And I am going to skip that last bit of working. So the half of v squared times 2 pi would just give me pi v squared. The half of v squared times theta times 0 would be 0, so I'm just going to get pi times v squared. Not that I need any of this to do the volume, I just wanted to do it properly. I could just use the properties of, frustrated cones to find the volume if I wanted to. And so now this is an ordinary integration. I'll do a third of v cubed. Now here's where I have to be careful, that's not a 0, so I've got pi times a third of 2 cubed minus pi times a third of 1 cubed. So pi times 8 thirds minus pi times 1 third would be pi times 7 thirds. And it's traditional to write it like this. Okay, it's apparently the answer. I could check that. I know the formula for the volume of a frustrated cone, so I'm just going to check. So it should be 1/3 times the height, which was 1, times the bottom radius was 2, and then the bottom radius times the top radius. So that's, which is 7. Oh, with a pi, sorry. Right. Cool, that works. Awesome. Okay. You might not know the formula for volume of frustrated cone, but it is my favorite 3D shape, so I happen to know what it is, just in case you're wondering. So if it has little r at the top and big R at the bottom and height h, the volume is 1/3 of pi h times r squared plus r plus r squared. Just in case you're wondering, it's cool stuff. Okay. Frustrated cone volume formula comes in handy finally. Some people call it a truncated cone. The official name is conical frustum, but frustrated cone is so much cuter. Okay. Compute the flux integral, the double integral over S of capital F, bold capital F dot ds for the vector field F of xyz is xy0. And the surface given by that. What? Just a second. For the... What? This is... What grammar? Okay. Complete the flux integral for the vector field F and the surface given by blah that is part of the boundary of W and oriented outward normal. So they just want the part of that surface that's part of the boundary of W? Or are they just declaring that this is the boundary of W?
Well, there's an inequality in W, and so if you look down, you get rid of the inequality, then you just get the boundary of that, which is...
Okay, so that actually is.
Yeah.
I don't understand the grammar of this and what it's trying to tell me, but I do know that S totally is the boundary of W. Oh no, just a second. No, it's not. They haven't told us to include the top and the bottom. Yeah. That really should have been a which, not a that. Given by this, which is part of the boundary. Okay. Okay, so let's just think about this thing. So this thing, let's see, S is okay, so we already went through a lot of thinking about what it was when it was equal to Z. And when it's equal to Z, equal Z is a circle, so I get circles of radius Z at heights Z between 1 and 2. Okay. The important thing is that it doesn't include the top or the bottom. It's just the outside. Because to get the middle here, I needed to do the less than or equal to 2 at that top level. So it's only the lampshade. It's not the top and the bottom. Okay. Okay, so the hint says, you may assume that W satisfies the assumptions of Gauss's divergence theorem, or you may compute the flux integral directly. I may choose to do both just to see what would happen. You wouldn't in the exam, of course. Okay. Now we also have a function of x, y, z. X, y, 0. All right. Okay. So, it distresses me that your lecturer didn't write this ds here in bold, because we're dotting it with ds, which means that this has to be a vector, because f is a vector, so we can only integrate numbers, and so we have to dot it with another vector to get a number. Okay. All right. Let's see. So just to point out, that's different from the way the curve worked, and I should have said it earlier. When I do this thing, I'm figuring out how much of the vector is pointing perpendicular to the surface, which seems completely opposite to the way that the curve works, because in the curve you're figuring out how much of the vector is pointing in the same direction of the surface. But it all works out properly, and it's fine. And it's something to do with the perpendicular to the surface trying to include both of the curves that are inside the surface. And in order to do that, you do the normal something like that. I'm making up words. I normally quote friends at this point. Look at you making up crap for me. But if you haven't seen that episode, then it doesn't make any sense. Okay, so, right. And so what we're going to do is we're going to find the integral across this surface of f dot ds. That's a capital S, because it's part of a surface as opposed to part of a line. So I'm thinking that this ds, which sounds like it should be the change in the surface. What the hell does that mean? And so the way to describe where a surface is currently pointing is with a normal vector. And so I know in my head that the ds is some normal vector times d something d something. Okay? Whatever the parameterization is. Okay? So in our parameterization, what did they say the parameterization was? V cos theta, V sine theta, V. Yep, that'll do it. We don't need the R, which was telling me what percentage of the radius I'm going, because I'm always at 100% because I'm right on the edge. Okay. Crap, I should write that down somewhere. S is also equal to theta is in 0, 2 pi, V is in 1 to 2. Okay. All right. So this is going to be d theta dV. Okay. The other way to deal with this is to do it as the cross product of the two derivatives of the function which goes from theta to and v to x, y, z. So I can name a function so if theta of theta v is like that, sigma, see sigma makes an S sound, S for surface, as opposed to gamma making a kurt sound, which is kurt for curve. So then I can do it as ds is like that. So the important thing is that this n hat is a unit vector. No, it's not. This is a capital N hat, isn't it? Yeah, dA, that's great. I love it. Like that? Is still there? Like that? Yes, okay. Unit vector of the multiplied by some sort of length which tells you the correct area. That's sort of the idea. All right, so this bit tells you the direction, and this is how long it is. Cool, and that length is to do with how much area is involved there. That's much better. Thank you very much. I can never remember this stuff. This is when I should probably look at the notes. I'm just doing what I would do in an exam. So the thing is that n hat is a unit vector. And this is some sort of idea of how big the area is. And the idea is that this thing here, like that's an infinitesimal area. This thing here includes both the n hat and the size part of the dA, this bit here. So in essence, I think the dA ends up being some sort of Jacobian thing with a d theta dv or something. In the end, this is what I know. So you can, if you like, if you know what the n hat is. Yeah. And so technically the n hat is this divided by its length. Rightio. Whatevs. Okay, so this I know to be true, so I can do this. Okay, so this is minus v sine theta v cos theta 0. Okay, because the v is a constant. And this is cos theta sine theta 1. And then when we cross them, oh crap, want the length of that, don't we? No, we don't, because we're going to dot it. All good. Because it's a vector and we have to dot it. Yes! So if I was adding if I was doing the integral of a scalar field, I'd need the length of that. Right. Good. Feeling much better. So that's, if it was a scalar field, that's when I do a ds without a bold on it. Because it's already a number and I can't multiply it by a vector. Okay. Good. Okay, and so when we do the cross product, we get, let's see. So in the first position we have that determinant, which is v minus sine theta. No, that's a 0. So v cos theta times 1, sine theta times 0. In the second position we have minus this determinant. So minus v sine theta times 1 minus cos theta times 0. And in the third position we have this determinant, which is minus v sine theta squared minus v cos theta squared. That's convenient. So we've got v cos theta, v sine theta, and sine squared plus cos squared would be 1, but we've got minus v sine squared and minus v sine cos squared, so that will be minus v. Okay. All right. Cool. occurs to me I should check if this is pointing in the right direction. Traditionally, it says here that we want it oriented by the outward normal. So I just want to make sure that this is actually pointing out. So let me just think about this. So this vector is on a circle of radius v. Okay. So circle of radius v, that's what this bit is, but it's actually down at minus v. And if we're inside our upside down lampshade, that's pointing in the correct direction. Okay. So this is pointing generally downwards, and therefore it's going the right way relative to this thing. Because of the minus v, it's going down. If it happened to turn out to be pointing the wrong way, I would just minus it. But you're supposed to actually do your cross product in the correct order to make sure it's in the right direction, based on the movement of the theta and the v. So I've got the theta first, so the theta's going around that edge. The theta's going around. Frustrated cone. The theta's going around that way. As theta moves, the point goes that way, and the v is going that way. So if I cross a vector pointing round that way and a vector pointing up, it's coming out of my palm and therefore going down. And so that's the correct direction. Whereas if I wanted it to go inwards, then I would need to do the cross product in the other direction so it points the right way. There you go. Okay. So it's pointing downwards, and so therefore outwards, and so therefore okay. All right. So we're good. Unfortunately, this f, if we're going to integrate it with respect to r and theta, to v and theta, we are going to need f to be in terms of v and theta as well. So let's see. F was f of x, y, z was x, y, and 0. So f of, now what was it? V cos theta, v sine theta, v is v cos theta, v sine theta, 0. And so therefore f dot ds is now coming out to, oh crap, just going to do it without it. I would normally do all of this in separate pieces on the exam, but I'm just feeling, uncomfortable at the moment. Of course, in the exam, I probably feel uncomfortable too, so I do them all separately. So, to be fair, if I was doing the exam for this, I would assume that I'd been in the course for the whole semester, and so I'd probably feel a little better than I am now. So the f is this, so we've got v cos theta, v sine theta, theta dot with v cos theta, v sine theta, negative v, d theta dv. Which is coming out to, oh look, v squared cos theta squared plus v squared sine theta squared plus 0. Which is just v squared. Yeah. Okay. And so therefore the integral I want is actually v squared d theta dv, and the theta goes from 0 to 2 pi, and the v goes from 1 to 2. I think that was right, wasn't it? Yes. Okay. Leaves. Okay, so that v squared counts as a constant with respect to theta, so a theta will just attach itself. And so I've got going from v equals 1 to v equals 2 of v squared times 2 pi minus v squared times 0, so that's just 2 pi v squared. And so I've got from 1 to 2. I don't need my v equals anymore because there's only one variable left, which is 2 pi times a third times 2 cubed minus 2 pi times a third times 1 cubed. Pi on 3. Yay. Okay. Cool. So what was actually happening there is a good question. We have a vector field that at every point produces x, y, 0, right? So at every point that has x, y, z coordinates, regardless of what the z coordinate is, it always just gives you the vector which is x in x, y, 0. So it points in the same direction that the point, damn it. So what was actually happening? The x, y, 0, here at x, y, z in space, there's the z-axis. The arrow points the same direction that was, but on the flat it doesn't go up or down because of the z equals 0. And when the amount of that vector that's perpendicular to my frustrated cone is just the further down the bottom you is, the less of it is pointing in the direction of the cone. Like when you're, this is sort of flatter and flatter. So the vector we have is pointing directly out, but we just want how much of it is perpendicular, which is that bit there, which is most of it. And then we add up all of those lengths across the surface here, and that produces like a volume. But to do that, we actually had to flatten out our frustrated cone to be able to do that. Yeah. Okay. And that's what all of those things add up to. Okay. Never sure exactly what that means. If they say flux, it's usually something to do with the amount of stuff that's passing through the surface, which makes sense for it to be a volume. You sort of go, well, you know, this is the direction, sort of the speed, this is like the speed and direction of stuff that's passing through, and so we just take into account the speed that's perpendicular, and that'll do it. Or it'll be a force, and there's like a momentum thing. I don't know how this works. It does help to understand what some of this means to have studied some physics. Possibly. Okay. So that's the answer we get for that. So I think if we were going to do it via Gauss's divergence theorem, we would need to take into account the top and the bottom. But the vector field is parallel to the top and bottom, so it'll produce 0 on those. Ah, that's fun. What if I did it by Gauss's divergence instead? So Gauss's divergence theorem says that if you have a vector function, no, it's got derivatives in it, right? So there's the triple integral across a volume of some derivative of some sort is the same as a double integral across the boundary of the original function. Now for this to work, using Gauss's divergence theorem, the original function must be a vector function, because otherwise we're not going to be able to use it for this. And there's a hint with the divergence that it's probably the divergence of f that we're adding up. So, yay. Divergence is the dot. Okay. And that makes sense, because if you yeah, cool bananas. So there we are. And this is the thing we want, except it's not our surface. Our surface has a bit extra. So I'm just going to go, this is going to be W, this is going to be the boundary of W. Is that how you write boundary in this course? Okay. Okay. Now let's just think about this. The boundary of W is S and the top circle and the bottom circle. Okay. And so when you do the integral across here, in fact, I should probably give names to those. So let C1 be the top circle and C2 be the bottom circle. And the boundary of W is SU, C1, U, C2. Technically the disk. I think the official name for a filled-in circle is disk. Because the terminology of circle is a curve. Okay, so the integral across the boundary of f dot ds is the integral across S of f dot ds plus the integral across C1 of f dot ds plus the integral across C2 of f dot ds. But C1 and C2 are parallel to f because f points outwards from the z-axis. So from the z-axis, and so therefore the integral C1 of f dot ds will be 0, and the integral C2 of f dot ds will also be 0. Okay. So therefore the integral of S f dot ds will be the integral over the boundary of W of f dot ds, which will be the triple integral across W of the divergence of f dV. Okay. Now, we went to all the effort of figuring out what dV is in terms of d theta, dr, and dV. Like it was that Jacobian. So we've already got that bit, and so it seems reasonable to convert our f into r, theta, and v. But I'm going to need to do the divergence first. So let's see, the divergence of f. Now, do each coordinate with the matching coordinate in the other. So just to be sure on this, this would be d on dx. Like that. Which is 1 plus 1 plus 0. Good. Which is 2. Okay, good, good, good. So therefore the integral across W of cross dV is going to be I don't know, 2 dV. Just a second, in part, whatever part it was, we figured out what the integral of 1 dV was, so this should just be 2 times whatever answer we got before. Which was 7 pi on 3, as I recall. Yay! Okay. Stylistically, sort of, in terms of the story I'm trying to tell, I haven't actually told the reader what the integral of f dot ds is, because equal sign only goes back to here, so I probably should have actually put in that here. There we go. So that was easier. You should always do the hint if they give you a hint, obviously. They're supposed to do it. But I did it the other way so that I could illustrate how doing surface integrals worked, which was the point of me, the questions that people asked. Oh, there's a D. Okay. Wow, packed all of the integrals into one question. Part D. Both sides of Stokes for F and S. Okay. Stokes' theorem has a double integral on one side and a single integral on the other. They both, all the theorems about integrals have more integrals on one side than the other. So Stokes' theorem that's a big S. That's a little s. I don't know if they're bold yet. I'm just going to get there. And it's got some sort of derivative in this position here, so that the derivative cancels out the integral in inverted commas. So some sort of derivative here. And the only other derivative that we haven't used yet is the curl, so I'm assuming that it's the curl. Apparently. Stokes' curl theorem. Beautiful. I wonder if when Stokes did it, it wasn't called curl. Somebody else.
And said, this is a cool thing, so he put it on the exam that year.
Yay. Naming rights because the first person who said it in a public setting. Good-o. And over here will be F, so I'm presuming that has to be that. I'm presuming they all have to be bold. Could be wrong. This is where I look it up. That's probability and statistics notes. I'm not going to find Stokes' theorem in there. Though you might need Stokes' theorem. There we go. Yes. There you go. Process of elimination. Love it. I now have ways of remembering what they are. I can start with the divergence theorem and work my way up, down. I'm just going to sort my pages. I've I never learned my lesson of numbering the pages. I'm just so excited about all the writing, you know. All right. Okay. No, we didn't. Okay. We did figure out what D bold S was earlier, so that's a good start. So let's do the left side. D bold S we figured out earlier, and it was that's using the parameterization we did before. So that was that was using V oh, crap of all crap. There were squares in there. No, there weren't. It's all good. All right. Sorry. No, I was looking at this cross product and going, no, this is squared, but no, that was here. That's all right. For theta from 0 to 2 pi and v from 1 to 2. Okay. Okay, so that's the left side. We're not done the left side yet. We still have to do del cross f. Like that. So the first one will be d0 on dy minus dy on dz, which is 0. And the second one will be minus d0 on dx minus dx on dz, which is 0. And the third one will be dy on dx. Wait, is this just coming out to 0? dy on dx, which is 0, and dx on dy, which is 0. Okay, good. We just confirmed that it all worked. I feel like this is not at all obvious from the way it's written what the answer should come out to be. So I'm just going to write in little things here. This is d0 on dx, sorry, d0 on dy minus dy on dz. And this is minus d0 on dx minus dx on dz. And this one is dy on dx minus dx on dy. Just so that a person reading this later will be able to see what working I did to produce that answer. Do you like my cross product method? I used to do it with determinants, but I just got confused. So I just do just the bottom two, and it works out fine. Okay. Cool. And so we're all good. We didn't even need to know what this crap was just here, because therefore the integral of s of gamma of del cross f dot ds is the integral over s of 0 dot ds, which is 0. That I know. Add up a whole lot of zeros, you still have 0 afterwards. Okay. So the right-hand side okay, so I need a parameterization of my curve. Now let's just have a think about this. This surface has two curves on its boundary, one at the top and one at the bottom. Okay. And I imagine that I don't necessarily want them to be pointing in the same direction. I don't know. I have to pick a direction to do them around. Is it like, it's like a standard direction for Stokes's? Just a second, I can do this. So Stokes's is about curl, right? And so if I point in the direction of the normal vector for my surface and think about the direction the curl is going when I do that, right, there's my surface, there's the normal, and there's the way the curl is going. And the curl is going that way at the top, which means I need to orient this that way. And at the bottom, it's going that way, which means I need to orient it that way. Right. So here we am, and the curl's going this way, which means I want the top one to be going the same direction the curl is, and the bottom one to be going the same direction the curl is. Yay! I knew there was a way of telling. Whatever. I can't tell my left from my right, so that doesn't help. But just so that everyone knows what the other David said, if you stand on the curve itself and with the surface below you,
your head should be pointing in the direction of the normal.
okay, so you stand on the surface with the surface with this pointing the direction your head is. Yes. See, that's way too much imagination for me. I wish you had those who you were watching had seen me with what I was doing just then. I should so record it. I should do it. Just a second. I'm going to try and do it again. Okay. So there's my surface, and I'm standing here. I'm going to go this way. Okay, so I go around there. Okay, great. It's not going to cut it in the exam, I don't think. Might get a bit upset at me if I stand up and... yeah. I'm just imagining also myself bringing a big bit of tape to the exam and putting out a floor graph like in the Maths Learning Centre. Okay. Good, so I've got my orientations right, and I can now, I need to parameterize them in such a way that their orientation is the correct direction, or just minus it when I do the gradient vector. Okay, so let's call the top curve gamma 1. Oh no, crap. Gamma is the function which produces the top curve, isn't it? It'd be really nice if I could use C, but I already use C for those other things, but I can pretend that it's a little c. I'll just write the 1 really big so you can tell it's a small c. Okay, so the top curve is going to be C1. And I know that it's a circle of radius 2. And actually, just a second, I had a parameterization for this surface here, and it's at height 2, so it's 2 cos theta, 2 sine theta, 2. Don't write down the answer yet. Now the problem with that is that traditionally a circle when I do it cos theta, sine theta goes anti-clockwise looking from above, and this one's going the other way. This one's coming back this way, which is clockwise. And so this is going the wrong way. So either I do it with this, and when I do the derivative, I minus the derivative, or I make sure this goes in the opposite direction, which means I could just do minus theta instead of theta, because then the theta is going backwards. It's going from 0 to minus 2 pi. Which is the same as just 2 cos theta to minus 2 sine theta 2. I did minus theta, so it's going clockwise. That's a did. All right. Okay, so the derivative of that, so for that curve, my ds is the derivative of this d theta. And so the integral around the top curve, which was C1, what's this thing called, f? Ah, damn it. Just a second. F was xy0, which in our case is going to be 2 cos theta sine theta 2. Oh, 0. Okay. All right, so the integral around the curve of f dot ds is going to be the integral around the curve. I really should have done the dot product first. I don't like writing integral signs a million times, so when we dot these, I'm going to get minus 4 sine theta cos theta plus 4 cos theta sine theta, which is 0. Yay! Well, d theta, I suppose. So the integral of curve 1 of f dot ds is the integral of 0 d theta from theta equals 0 to 2 pi, which is 0. So I'm presuming the other one's going to come out the same way, which sort of makes sense because the actual direction of the curve... No, it doesn't actually. Yes, because the direction of the curve is perpendicular to the... the f is pointing out, f points outwards, right? And the curve, as you go around it, its tangent vector will be pointing sideways, and that's perpendicular to the other one. And so since you're dotting them, you get 0. Ah ha ha. Okay. So the bottom curve will be 1 cos theta, 1 sine theta. And ds will be cos theta 0, d theta. F will be and f dot ds will be minus sine theta cos theta plus cos theta sine theta plus 0, which is 0, and so therefore the integral over C2 of f dot ds is the integral of 0 d theta, which is 0. I didn't have to change the orientation of this one because it's already going the correct direction. And so the integral across the boundary of ds of f dot ds is the integral of C1 f dot ds plus the integral C2 of f dot ds, which is 0, plus 0, which is 0. It would be much more satisfying if they were actually like one of them was 2 and the other one was minus 2 or something, and they cancelled each other out. But that's okay. I was still excited by the fact that we got 0 for 2 different reasons. One of them was because the perpendicular to the surface was in the same direction as the vector field, and we were crossing them. And the other one was because the tangent to the curve was in perpendicular to the vector field, and we dotted them, and we got 0 for both, but for opposite reasons. Though this theorem would seem to say that they're actually the same reason. Yeah. But that's the thing with theorems that connect derivatives and integrals. They connect things which didn't seem obviously connected before. Like derivatives and integrals are not obviously connected at all. It's unobviously connected, which is why we need theorems to connect them. All right, I feel like I've learned a lot about this. How does everyone else feel? I still have, I don't know, another 15 minutes if you want me to talk about something else possibly related to this.
I think for me the thing that's helped me the most is actually finding parameterizations.
Yeah.
For various, so this question was okay because they gave us parameterizations
Let's find some parameterizations. The exclamation mark means it's a musical and I'm going to be singing it. No, sorry. You don't know that, so there's a musical called Oliver with an exclamation mark, and you know it's a musical as opposed to just an ordinary film because it's got an exclamation mark on it. That's why it should be called The Greatest Showman. Okay. All right. I'll see how I go. Parameterizations, there is a classic basic parameterization, which is the parameterization of a circle. So for your classic circle of radius r has parameterization r cos theta, r sin theta. Like that. Classic parameterization of a circle in 2D. That's the thing that most of these parameterizations in an exam seem to be based on my experience. Okay, and the important thing to know about this is it goes anti-clockwise looking from above. Okay, that's just the edge of a circle, or the inside of a circle. Of radius r. You've got two choices for how you want to play this. One is to make it look exactly the same as the other one, but we might need to change our letter to something else. Oh, damn it, that's going to be annoying with the sign. P is a good number. Sorry? Good letter. For P being between 0 and r, and theta being between 0 and 2 pi. And the way that this parameterization works is that you pick a radius and then you pick a position around the circle of that radius. So what we're doing is that we're picking a particular radius and then picking a circle around that radius and then maybe picking another one, and it's being made out of all of these little circles joined together. Okay. The other choice is to do what your lecturer did in that past exam, and to say what percentage of the radius you've covered so far. So you could do still your r cos theta and your r sin theta, where r is a fixed number, right? It's like 2 or 7 or minus, no, not minus, 2 or 7 or 215, and just pick a p to multiply it by, and this time the p goes from 0 to 1 because it's the proportion of the radius you've covered so far. So in this one, p is the current radius, and in this one, p is the proportion. There is no r in that position in proportion. Is the proportion of the radius you've covered so far. And that's two different ways to parameterize the inside of a circle. Without having seen that past exam, I wouldn't have thought of that. But now I've seen it, I know it. I might put a direct link on the website to this part of the seminar when I do it, if you want to get to this bit. Okay. So they're the classics, and pretty much every one of the ones I know that are useful are based upon that. But there are some about the surface of a sphere as well. But let's go into 3D now. Oh, just a second, a line. I'll just go into 3D. So the third one that's important is a straight line. So a straight line that joins 2 points. I'll just do it as an example. This is point number 1, this is point number 2. This is not an example, I'm just going to run with it. The straight line that joins those 2 points, well, it starts at point 1 and then you go some percentage. I should have used t back there, that would have been cool, that would have been all consistent. But anyway, some percentage of the vector that goes from P1 to P2. For t in 0 to 1. I'll do an example of that, right? E.g. line from 105 to 351. So I can say the vector like that, which is 2, 5, minus 4. And so the parameterization x, y, z is beginning vector plus t, beginning position plus t times the vector between them. Classic. So that's straight lines. There are other ways to do it, but this is the quickest way. And the important thing to realize is that the lines are directed. So if I was going from 351 to 105, I would be starting at this one and my vector would be minus this because it's going in the opposite direction. Okay. Anything else that's not those, they'll probably give you the parameterization. I mean, there's one with like a spiral going upwards, but I can't remember. It's got like a circle bit and then like a z bit that increases as the theta goes round. So, well, that's just, this is not one that you have to remember, but let's do it. That's very soft, I'm sorry. And this is in 3D, by the way. So let's say we've got a radius of, say, 5. This is just an example. So I've got a radius of 5 of my spring, and passes through 500. Just got to have a starting point. And the turns are like, maybe the turns are like 1 apart. I don't like 1. I will do 2 if that's okay, because I don't want the 1 to go missing when I do the parameterization. You can't see where it is. Okay, so you know, looking from above, it's a circle. Like that. And as you track around the spiral, each loop should be 1 pass around the circle. And so I should go that every 2 pi gives me 1 piece of the circle. Okay, so let's see, every 2 pi is 1. Of the circle, of this circle. I should really pick an ending point, shouldn't I? Let's say it finishes at 10, no, 5, 0, 10. Yeah. Five, 0, 0. Let's see. Damn it, that's not 10, that's 8. There we go. It's got 4 loops, and there's a loop every 2, right? So Okay, every 2 pi is one loop of the circle, and it goes 4 loops total from, because there's a loop every 2 in the z direction, and so it goes from 0 to 8, so there must be 4 loops. To 8. Loops are 2 apart, so that's 4 loops. And so it looks like I'm going to need my theta to go from 0 up to 4 lots of 2 pi. Because that's 4 loops total. I'm going to go round 4 times. Okay. I'm making all of this up. I've never done this before for a helix. I'm just figuring stuff out. Okay, but I need something. So my x and y coordinates are totally going to be 5. I'm totally going to have my x and my y. Totally going to have my x and my y to be 5 cos theta, 5 sine theta. Don't know what goes here yet, because it just keeps going round and round that circle when I look from above. So looking from above, the x and the y coordinates are totally going to do that because it's going in circles. I just need something here that's going to go up. Okay, so every time I go around 2 pi, it's supposed to go up 2. So let's see. So I need the z coordinate go up 2 when theta goes around 2 pi. So if I do theta divided by pi, that would work. So if the z was equal to theta over pi, that would work. Sweet! Okay, so we've got our parameterization. Five cos theta, 5 sine theta, theta on pi. Yay! Rightio. That was fun. So the thing that made me be able to do this is thinking about it, looking from above, and knowing that it tracks around this circle. So the x and y parts had to just be a circle. And then I just had to figure out what the z bit was. I also had to know how many turns around it went, but that was me calculating things. That was so much fun. I've never done that before. And so now I could figure out the length of this helix by integrating this, integrating one of this. I'd need the length. Ooh, no, I don't want to do that. I need to talk about more parameterizations. As fun as that is, I need to make sure this fits on the video. But just as an aside, the length, I won't do it. So the length will be, let's call this gamma. The length will be the integral of from 0 to 8 pi of 1 times gamma dashed theta, the length of the length of gamma dash theta d theta. And that will be how long that is. It's so cool. Makes me want to see. There's this puzzle which goes, you know, you wrap tinsel around a Christmas tree, and it gets wider as you go. And if you've got a Christmas tree of a certain height and radius, then how do you know how much tinsel to put on? How long the tinsel has to be? And you could do it if you were able to parameterize a spiral around a cone. I'm not sure how to do that yet. Anyway, if it was a Christmas cylinder instead of a Christmas tree, I'd be good. Depends on the shape of your tree.
I read this book somewhere which said that you just need to know if you have a helix around a cone, like this the helter-skelter and the slides.
Yeah.
You just need to know the radius halfway up.
Ah, well, I'm sure you do. There's all sorts of, it's like a frustrated cone thing where you do the average of the top and the bottom. I'm sure. Now, anyway, another day. So, sphere. So the point of these, remember the point of these parameterizations is to find ways of figuring out what position you're at so that you don't need to know what any of the variables are to figure out what other variables are. So you can do parameterizations that allow you to say, oh, well, if I'm at height 2, then I have this zone, this range for what I can do. You don't want the range for the variable to change when the other variables change. That's the point. Okay, so there's our sphere. I'm going to center it on the origin. And I'll do it radius capital R so that I can keep some other things. Okay. So, this is just the surface of the sphere. So the surface of my sphere, I need to be able to pick, I only need two variables, and I should be able to pick those two numbers independently of each other. So I think, well, I can cut it into circles, certainly. I can go round circles at various heights. That's totally something I can do. So if I can pick a height, I can go round a certain height with that. And then I need to know how far up and down my circle is. So I can pick a Z if I want to do that, but it's easier to pick an angle to know how far up and down you are. And I believe you pick the angle, depends how you want to play it. So you can pick the angle just from the top down. I think that's the tradition, to pick an angle down. So you go an angle down like that. Okay. So I know that at a particular height, so I know it'll be something cos theta something sine theta times whatever the height is. Definitely know that. And where theta is the blue angle here, that tells you how far round the circle you are. And what I need to do is I need to figure out what the correct height is, what the correct radius is for my circle and what the correct height is. So if I do an angle, now I'm going to look this from the side. So here's my blue circle that's coming along here. And here's my angle coming down. Let's call that angle phi. Okay, so if this is the radius here, it'd be much easier if I chose phi going from the center up and down. That'd be way easier. That's all right. So this distance here is r cos sine phi. And this distance here is r cos phi, up here. Just to color code. Like that. And so it looks like the radius at angle phi is r sine phi, and that goes in this position. And the height at angle phi is r cos phi. So we have that the parameterization is r sine phi theta. The phi goes from 0 to pi because I'm tracking from the top of my circle down to the bottom, and that's only 180 degrees. Because remember, when I get this point, I go all the way around the circle at that point, so I don't need to come back up again because I've already covered both sides. And the theta goes from 0 to 2 pi. There we go. That's the parameterization of a sphere. Right. I reckon I've only got a couple of minutes to go. So how about we do like a paraboloid? do that one. Z is x squared plus y squared from 0 to 5. Okay, so at different z's, x squared plus y squared equals a particular z. That would be a circle, and the circle's radius increases as z increases. Radius is root z. And so certainly something like this, but it's curved, and the reason I know it's curved is because the radius is not equal to the actual height. And so when I'm at height 3, the radius is root 3. When I'm at height 4, the radius is 2. When I'm at height 9, the radius is 3, and so the radius increases slower than the height does, which is what causes it to be curved like this. Damn it. Okay, but it is a circle at every height, and so I can use my r cos theta, r sin theta thing at every height. So we can certainly do that. And then I just need to figure out how high that is based on something, and I might as well just use z. So I can say that it's definitely something cos theta, something sin theta at each height. And if it's at height z, I can just use z if I want, but traditionally you don't use the same letters that you used in the others, so if you want, that'll work fine. I don't really want to square root, do the derivative of a square root, so I might change this in a second, but this is one way of doing it. So you pick a height, and at that height the radius is r h cos theta, h sin theta, and crap, other way around. Sorry guys. That makes more sense. Sorry about that. I pick a height and the radius is root h. So h goes from 0 to 5 and theta goes from 0 to 2 pi. Or could have done it that way and just sort of called that g squared is h, and then the g goes from 0 to root 5. And the reason why you might choose this one is because it's easier to differentiate than this one with respect to the h. All right. So I'm hoping that I'm getting something through about how I go about trying to choose these things. Usually I look for the circle first, and then that helps me to figure stuff out. Other ones I'm not 100% sure. If I want to do the full inside of the sphere, then I might use my percentage thing that I did earlier. So I would so my sphere volume, well, I had one before. What did I have before? I had r sine phi cos theta, r sine theta sine phi, r cos phi, and I might put a proportion there. So I'm just copying it from here. This was my parameterization of a sphere. And this, remember, told me the position on a circle. And then what I might do is go, well, I need to choose how far in I am So this is the proportion of the radius at this height. And so in that case, I'll have the p going from 0 to 1, because it's a proportion, the phi going from 0 to pi, and the theta going from 0 to 2 pi. That's a really neat trick. I like this trick. I'm just going to put that next to the sphere in my notes. So we can now use that trick to do the volume inside anything. It's fabulous. Love it. Okay. I don't know any others off the top of my head that I could do. I mean, a cylinder I could do. It's got circles in it. But the cylinder's way easier than the sphere. So why don't I do radius 3 from z equals 1 to z equals 8. Well, I know that at every height it's 3 cos theta, 3 sine theta. And the height goes from 1 to 8. And that's it. Yay. I mean, the actual original equation of this would have been something like x squared plus y squared equals 9. That's what that would have been. So it's important for you to be able to look at an equation and be able to tell what it is. This is an equation in 3D. It doesn't involve a z, which means it's the same thing at every height, which makes it a cylinder. Whereas this thing was different radiuses at different heights, which means it's not a cylinder. And the sphere would have been, you know, x plus y squared plus z squared is r squared. The only other one I know that you probably aren't going to come up with, because you can't actually do most of the integrals involved, is an ellipse. So I have a parameterization for it, but most of the integrals that you want to do about them are impossible. So I'm going to show it to you anyway because it's nice. So this is minus a and minus b and b. And I believe it's that. So with a circle, you just use the same radius for the cos and the sine. But for a sphere, for an ellipse, you use the x radius for the cos and the y radius for the sine. And it magically works. If you want your center to be in a different spot, then you'll have to shift it over. But almost to every exam question people have asked me about in the last 10 years has been centered at the origin. And so I wouldn't worry too much. But if you want to move anything anyway, you just add the appropriate coordinates to the coordinates. Just remember that if you're changing an equation, you subtract, and if you're changing the coordinates directly, you add. So if this was centered at, and this would go for any object at all, if this was centered instead at like 3, 2, for example, so that one there, it's got radius 1 in the y direction and radius 3 in the y direction. So that's going to be a 3 cos theta and a 1 sine theta. But it's centered at the point 3, 2. Yay! So that's It's very similar to how the line works, where you've got a center and then a plus t of something. Same deal. You've got a center 3, 2, and then plus the other bit. Yeah. I hope that helps. Yeah. Cool. Well, I'm going to stop there because I have to get home at some point.